Okay, so we've got this function here. What do we observe about it? Remember, it's all like how we approach, how we proceed has to do with observations we make. Very nice. That's important to look at. And what does that mean? So it's one thing to observe that. It's another thing to remember what it means. Go ahead, Cassidy. Nice. How do you remember that? Do you just memorize it? Good. Anybody else? Yeah, I see you. Very nice. You won't be able to find a horizontal asymptote. Why else? Anybody else? One way I think of it is when you have a horizontal asymptote, what do we have to do? We have to do the division, right? So I can divide the denominator into the numerator because it has a lower degree. When we did long division and synthetic division, it was always we're dividing something of a lower degree into something of a higher degree, right? So that's another way you can think of it is like this is the case where you actually can divide, right? You could think of it as when you have a horizontal asymptote, if the degrees are the same, this is kind of like I think what was said already, but are along the same lines. When you have the degrees are the same, you find the horizontal asymptote by looking at the coefficients. When the degree on top is lower, that means it's 0. You have a horizontal asymptote at 0. So you could also kind of remember those two, and oblique asymptote is the other kind. I don't know. There's lots of different ways to think about it, but it's definitely something you have to do. In this case, we're going to come up with all the different sort of versions of this function first before we go. Like last time we were going ahead and finding intercepts and stuff like that. But this time we're going to rearrange and put everything in the nice forms first and then look at what we have and then decide how to proceed further. So what are we going to do to get a better sense of what this function is like and behaves like? Yeah, we're going to factor everything. What do I notice about the top when I go to factor it is I think it's the first one we've seen. Well, we did have the one that was, it was a difference of cubes, so it was easy to factor. But this is the first cubic that's like, we have to actually use one of our factoring techniques. So go ahead and do that. However you choose, use factor theorem or whatever it is that you think works best for you. In this case, you kind of have to use factor theorem, whether you actually use synthetic or not in the end. Or just use our little trick. I'm going to go over this one more time because, I wonder, a lot of people probably didn't like this method earlier or didn't quite pick up on it, never quite clicked. But now that you've done a lot of more work with this kind of algebra, maybe it will click. And when you're doing a curve sketch, it takes so much time that it really helps if you can shave a minute here or there. So if you can avoid, it also will save some space on your paper, like not having to sort of have a whole section of your page devoted to synthetic division. But it's fine to do synthetic division if you have to, and you'll kind of do a bunch of pre-work probably at the top of the page, and then maybe even like sort of draw a line and start the rest of the solution after that is something you could do. Anyway, so if you want to just watch, I'll remind you how this works. So it's all about, we've got enough information already right here that if I think about what I'm expanding to, right? When I do this times this, I'm going to get that. So it's all about my understanding of expanding that allows me to, once I have that factor, we couldn't do this in grade 10 because we didn't have the factor, but with factor theorem we can do this, okay? So the first step is pretty easy. This times something has to give me the x cubed term. So that one's pretty obvious. It's just going to be x squared. The other thing you might think of is this is going to be 3 terms because it's going to be a linear times a quadratic, or at most 3 terms, I should say. It could be that there's like a 0 term in there, but it's going to be a linear times a quadratic, right? So it's going to be x squared, x, and constant. That's what it's going to look like. So then what do? I say, well, -1 times x squared is -1x squared, and x times something is going to give me the x squared term. So all I have to do is figure out what this is. So when I multiply it by x and add it to -x squared, because that's what I get when I multiply there, gives me -2x squared, and it works out to -x. And again, I can go back because that's -1x squared, that's -1x squared, and together that's -2x squared. Right? So you're thinking about when I expand, the cubic term only comes from one place, the highest degree in this case, but these middle terms come from multiplying 2 things together. Only, right? There's only 2 things that are going to give me an x squared term. That times that and that times that. When I add them together, it's got to give me this. So I'm just using that understanding of expanding. And then the last term I can get just from -1 times something has to give me +6. So it's obviously -6. Okay. And we're writing the whole function. So I've got to do the bottom 2. I'm gonna factor the bottom because I might as well at this point. X plus 2, x plus 1. Yes, they are. Thank you very much. Oh, you cut them up for us. Thank you. Okay, and then one last factoring here to do. And what do you notice? Anybody? Yeah, we've got some things that divide here to 1. And what does that mean? We have a hole, a hole at, x equals -2. Because it divided on top and bottom. The reason why it's a hole is because if I plug -2 into that equation, it doesn't matter what these things work out to, right? -2 minus 3, that's -5, but that won't matter. What matters is I get 0 over 0, right? That's what ultimately matters. And 0 over 0, you can't do it. But 1 over 0, as we approach 1 over 0, that approaches infinity. 0 over 0 doesn't. The zeros kind of almost cancel each other like as you're approaching it. So it's not an asymptote because it's not 1 over 0 or 2 over 0, it's 0 over 0. So it ends up being a hole, okay? So we've got a hole there, And I'm just going to say, therefore, f at x equals x minus 1 times x minus 3 over x plus 1. And we just want to remember that it has a hole. That's an easy thing to forget later on, because everything we're going to do from here on in, remember what I've said. This function behaves like this everywhere except at that hole where it doesn't exist. So I can ignore all of this stuff basically, except I have to remember that hole. And if you forget it in your final sketch, I mean, you're going to lose a mark, but you know, we've ignored the actual function that we started as. But it's kind of nice because now all the math I can just do with this easier expression, right? So everything we do, you're going to notice, is from this simplified form. That's one of the main reasons why we simplify things, because it does make the work more simple from here on in. But I got to remember that hole in my final sketch. And then I'm going to expand this because, like I said, we're going to do like the whole, all of the algebra here first. So we've got all our nice forms. And then as we're working, in some cases we'll use one of them, in some cases we'll use the other. We'll kind of flip back and forth, whichever one's more convenient for the math. Whichever one you like punching into your calculator more, maybe. In this case, I think in this question, we can, if you can do some of it in your head, you can get away without the nitty-gritty calculator stuff for the asymptotic behavior, but everybody's different. Everybody okay so far? Okay, so that's all the pre-work done. Now we're going to get into finding the properties. So we usually started with the intercepts. We're going to keep doing that. So the y-intercept, I'm going to use the second version over there. So it's 0 squared minus 4 times 0 plus 3 over 0 plus 1. So that's 3 over 1, which is 3. My y-intercept is 3. And my x-intercept, when 0 equals x minus 1, x minus 3. So my x-intercepts are 1 and 3. When the bottom is 0, I get a vertical asymptote. When the top is 0, I get an x-intercept. Don't get those backwards. That's where our understanding comes in. You don't have to memorize. You just think about it. When the top is 0, the whole thing is 0. If the whole thing is 0, that's an x-intercept. When the bottom is 0, I'm dividing by 0, but I can't divide by 0. That's what gives us an asymptote. Unless it's whole, we already talked about that. Okay. That's our intercepts, so let's do our asymptotes. What do I know about horizontal asymptotes? When I have an oblique asymptote, we don't have one. We don't have a horizontal asymptote. We will have vertical asymptote. Okay, you could have more than one. In this case, we only have one. So, and we usually start with the vertical asymptotes first anyway. So my vertical asymptote is x equals -1, and I have to find the behavior around that asymptote. And then again, this is where like behavior around vertical asymptotes, horizontal asymptotes, and oblique asymptotes, the test is all a little bit different. The thinking's the same, but the testing is all a little bit different, right? So for a vertical asymptote, remember, we're always picking x values, and you want to pick an x value that's going to give you a sense of what the function is doing. So what kind of value, x value, is occurring when I'm near a vertical asymptote? Close to the asymptote, the value of the asymptote, -1 in this case. I personally always like to start going left to right in my head to really focus my thinking, manage what I'm thinking. So I'm going to do -1.001. Thinking from left, I'm in the negatives, so I'm past -1 into the negatives, right? Doesn't matter what you start with. If you start with if you get mixed up and you start with negative 0.99999, that's fine. You just got to know you're to the right of the asymptote or the left of the asymptote. Just do it this way every time, and then you're good. Never, you could get away with negative 1.00. No, sorry, that's the same. 0.1, but you can't go any bigger. Like negative 1.1, no. Okay, so go to 100th or 1,000th or more, but I don't know why you would ever do more. Okay, does that make sense? And just for yourself, pick a value and do it the same way every time. So when I do this, I'm going to go ahead and look at this one. And when I'm doing this math in my head, what I'm thinking is, essentially, is that number bigger or smaller than the number that it's being added to? And that's going to tell me whether or not the whole bracket becomes positive or negative. Right? So I take a negative number and I subtract something, that's still going to be negative. That's easy. Take my negative number again and subtract something, that's negative. So the two brackets on top are going to be negative. Does that make sense? Then when I take this negative and I add one, well, that's still negative because this value here is slightly bigger than that value. That's the value that gave us our asymptote, by the way. So we already know, we've already thought about whether this is bigger or smaller than that number, right? Kind of already thought about that. So negative 1.001 plus 1 is still negative. And all we care is that that's negative. And that tells us as x approaches negative 1 from the left. That's what we thought of already. We started from the left and we're working left to right. Y goes to negative infinity because my value is that I got, my outcome was negative. Okay, do the same thing for negative 0.999. And I get negative minus something is negative. I get a negative minus something else, that's negative, so they're still negative on top. But here's the difference. I've crossed over to the other side of that value, so negative 0.9999 is smaller than 1, so when I add 1, it's going to be a little bit positive. Okay, so that's going to be positive. And as x approaches, that's not an x, that's weird. As x approaches negative 1 from the right, y goes to positive infinity. Okay? Sure. Any questions so far? All right, let's do our oblique asymptote. First thing we have to do for our oblique asymptote is find out what it is. We have to find the equation of the oblique asymptote. That's what we do with the other ones as well. It's just more trivial to find the equation of a vertical asymptote. Finding the oblique asymptote equation takes a little bit of work. And so what do? We go back up and take a look. Like when I'm doing the division, I've got to use this form, so it's handy that I have that form already done for me. And what I'm doing is I'm actually dividing x plus 1 into I'm actually dividing the denominator into the numerator, right? So x plus 1, and I'm going to use synthetic division, 1, negative 4, and 3. Bring down the 1, multiply, subtract, multiply. 3 minus negative 5 is 8. And there's my remainder. Write your division statement. This isn't f at x, because f at x, it was when we first learned this, But it's not now because f at x is the function we're sketching. My first statement here is x squared minus 4x plus 3. So it's like this thing, right? Equals x plus 1 times x minus 5. That comes from the quotient, the result that we got. That's not a 5. What's going on with me today? Holy cow. And then my remainder, so plus 8. We okay with this? And that means f at x, remember f at x, we've set this up in this particular way. F at x is this expression over that. That's what our original function was. That's what it simplified to, minus the whole, right? But this is the same as that. And this expression that we've come up with, which is like our division statement, is useful for when I do this. When we did this the first time, we wrote that whole thing over x plus 1, and then that looks very similar to what our original function was. But then we like to split it up into 2 because this is the whole point of what happens is that right there, and you end up with that. It's very strange. Like, if you plugged that into graphing software, that's the function. That's not, that statement right there is not the asymptote. That's still the function. It doesn't look anything like what we know as rational functions. It's not a nice, this wouldn't be a good way to sketch, but that's the actual function. If you plug that into graphing software, it would look like the sketch we're going to get, right? It would look like this, or it would even look like that original thing that, right there that we started with, just it wouldn't have the hole because it's missing, right? But this is useful because now my oblique asymptote is y equals x minus 5, and my remainder part is 8 over x plus 1. The remainder part is important to have because that's what we're going to use to do the testing. Remember what it means. Maybe after we get the sketch done, we'll try to talk about it, but to me, what this is saying is that when x gets really, 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 really big, my function, my original function, basically looks like this, except there's a tiny little bit that we're adding to it. Otherwise, it basically looks like that line. Okay, when x is really, 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 really big, this is going to be 0. And so the graph will be slightly above or slightly below if you're adding or subtracting, depending on whether it's positive or negative, but otherwise it basically looks like this. So that's why that remainder part is really important. So then we usually do this, right? The slope is 1, the y-intercept is negative 5, and the x-intercept is positive 5. And we can do our behavior testing. I hope I have enough space here. So I've got, let's see, f at, now we got to remember, how do I do the testing for an oblique asymptote, right? So we did the vertical asymptote, that worked out one way, we did one type of thing. Horizontal asymptotes, we do another type of thing. Oblique asymptotes, what do we do to test? I kind of already gave it away. We put in big values of x because that's where that behavior is happening. When I'm way, way, way far out in the positive x's and way, way, way far out in the negative x's. So we'll start with negative 1,000. And when I put this into the remainder part, it's 8 over 1,000, negative 1,000 plus 1, so that whole thing is going to be negative. So we are below. We're approaching it from below. And when I put in positive 1,000, it's 8 over 1,000 plus 1. So the top is positive, the bottom is positive, so the whole thing is positive. See how you can do that in your head? Therefore, here it's approaching from above. Any questions? I believe that's all the work that we needed, and now we can go ahead and sketch. You may not have enough space on your page, so you can do it on the next page. I think I have enough space here. All the work that we did was finding values that we need to mark on our graph. So I got to mark the asymptote, the asymptotes, however many we have, all the intercepts. The intercepts of the oblique asymptote only to graph the asymptote. Okay. Again, your graph doesn't have to be perfect, but what you want to be careful of is stating things that aren't true with your graph. So if your curve crosses the x-axis somewhere that it's not supposed to, you're losing a mark. Okay, that's the reason why we find our x-intercepts. Or if it doesn't cross somewhere it is supposed to, you're going to lose a mark. If your curve does something weird that it's not supposed to, like some kind of turning point or twist or something that shouldn't have that, you're going to lose a mark. Or I equated this to when you're doing parabolas in grade 10, and instead of drawing a parabola like this that we are very familiar with, people draw them for some reason like this. I don't know why. But like, that's not the shape of a parabola, so unfortunately you're losing a mark or half a mark or something like that. Or people love to make them turn back in, which they don't do. Okay, so just be careful. Okay, so I'm going to make this horizontal asymptote, or sorry, vertical asymptote really close to the axis, just because I think it's going to work out to be helpful to be very close. That's x equals -1. And then my oblique asymptote, I'm looking at the intercepts for that are at +5. So that way I can go about 5 times as far and make it about the same. So here's an example, like if you put this one way out here and this one here, that's not actually wrong because maybe your scale is different, so I'm not going to take a mark out like that, but something that's worthwhile thinking about is where approximately you're putting your intercepts. Okay, and I'm going to use a ruler for this. So that's my oblique asymptote. It should be dotted, but it's hard for me to do that on the computer. And then I'm going to mark the intercepts of my function. So I've got a y-intercept at 3. And I've got x-intercepts at 1 and 3. And this is kind of nice because all the behaviors I need are basically right here on this screen. So I'm looking at this one. As x approaches -1 from the left, y goes to -infinity. So that's coming down here, right? As I approach from the left, it's going to go to -infinity. And then as I look over here, when x gets really big, what does f at x do? It's just below the oblique asymptote. So it's going from below, it's going to turn, and it's going to go down like that. So now I can draw that curve. And then same thing looking at the other two statements. As x approaches -1 from the right, y goes to positive infinity. So that fits sort of how I'm visualizing this graph. And right here, as f goes to positive 1,000, it's above the oblique asymptote. And I've got to go through those intercepts, right? So this is gonna be a little bit tricky, but I'm gonna come down like this. Something like that. That wasn't very good, but I think maybe my scale's off a little bit, and it was hard to get it to approach. In fact, in this case, I would probably do this. I would probably move this guy over a little bit so I can make that look a little bit nicer. Whoa. So I'm going to move this over a little bit, and then I can kind of come down a little bit further. And then up here. Should be even a bit smoother than that. Okay, I think we've got everything. Yes? Say that again? Ah, thank you very much. What did I say? Don't forget the hole. And then what did we do? We almost forgot the hole. So the hole, I'm just going to scribble here for a second, is at -2, I believe. So it's going to be right around here. So what we're actually going to do, I'm going to have to redraw this curve, is put my hole in and do like that. So that's what a hole should look like. It's an empty circle. Again, you want to be doing this with a pencil 100%. And that way you can erase and draw the hole in after. You don't have to redo the whole line, obviously. Any other questions?